Our study of sequences from this point on is going to focus almost exclusively on their asymptotic behavior. Asymptotic behavior is a general term in mathematics that refers to what happens to something in the long run. And you've seen examples of where you studied asymptotic behavior in the past. For example, if you go back to algebra and you looked at some function, say f of x is equal to 1 over x, what happened to the function in the long run meant really what happened to the function values as x went to infinity. And when you got to calculus, you saw how to address that. You took the limit of the function as x goes to infinity, and you were able to evaluate that, and you found out that that limit converged to 0 from above. So this tells us about the asymptotic behavior of the function. So notice that the limit as x goes to infinity not only tells us about the asymptotic behavior of the function as far as just being able to evaluate that limit, but it also kind of gives us a picture of what the function's doing. We know as x goes to infinity, the function values remain positive, but they're getting closer and closer and closer to 0. Now, if we apply this same logic to sequences, we showed before that a sequence is a function of the natural numbers. So doesn't it make sense to think about what's happening to the sequence in the long run in terms of what's happening to the sequence as n goes to infinity? And of course, how we address that is we can take this limit. So the limit of n goes to infinity of the function for the sequence is going to tell us about the asymptotic behavior of the sequence. Now, it turns out that sequences can have a lot of different types of asymptotic behavior, and I want to just illustrate a few of them here. If we go back and we think about the examples in the last video, the first one was a geometric sequence. And if we take the limit of that sequence, we see it converges to 0. That limit's equal to 0. So whenever the limit of a sequence is equal to a real number, we say it converges to that number. So in this case, we would say x of n converges to 0. And that's the notation we would use. However, a sequence does not necessarily have to converge. And if we look at that second example we gave of an arithmetic sequence, we see that when we take the limit, we end up getting an infinite limit. So here we do not say that the limit converges to infinity. Converges is reserved for a limit that's equal to a finite value. Here we say it diverges, and more specifically we would say that it diverges to positive infinity. Now it's possible for a sequence to diverge but not become infinite. And this last example we saw of this alternating sequence is a good example. Okay? The terms are bounded, so they don't diverge to positive or negative infinity. But notice that the limit does not exist. And when that happens also, we're going to say that the sequence diverges. Now you might ask, well, why are we interested in the asymptotic behavior of sequences? And it turns out that they really are the cornerstones of calculus. We can understand all of the main concepts in calculus purely from the point of view of sequences. And I want to illustrate that by showing you how both the derivative and the integral can be thought of purely in terms of sequences. So if we consider the derivative first, we might be interested in the derivative of some function f at some point x equal to a. And we know that geometrically, the derivative of f at a is equal to the slope of the tangent line at x equal to a. But how do we get the slope of that tangent line? Well, you might recall what we did was we set up a sequence of secant lines where this other endpoint of the secant line kept moving closer and closer and closer to A. And what we did was we looked at the slope of those secant lines. So we had a sequence of the slopes of the secant lines. And what we showed is when the derivative exists, these slopes converged to the slope of the tangent line. In other words, the limit of the slopes of the secant lines converged to the slope of the tangent line, which we know is equal to the derivative of the function at that point. So again, the notion of a derivative can be derived purely from using sequences. And the same is true of the integral. If we think about what an integral is, okay, an integral geometrically is the area under a curve. And so we can generate a sequence of areas that converge to the integral by continually making the subintervals that we use to get these rectangles and compute these areas smaller and smaller. So when we have a large subinterval, we compute the area under those rectangles, and that's the first term in our sequence. Then we make these subintervals smaller, so delta x2 is smaller than delta x1. Compute the area under those rectangles, we get the second term in our sequence. Make it smaller yet, we get another area, which is a third term, and so on and so on. So now we end up getting a sequence of areas. And we showed that when the integral exists, the limit of those sequences converge to the value of the integral. So again, integration can be thought of purely in terms of sequences. Now, let me just outline very briefly how we want to study this, because it's a kind of long topic. We're going to go through this by looking at 5 different videos. This is the first video where we're basically just introducing the notion of asymptotic behavior and what it means. The 4th video is going to talk about some basic properties that tell us if a sequence converges. In a sense, that's the most important question. The next 2 videos are then going to talk about the techniques we can use to determine the limit of a sequence once we know it converges. And then finally, in the last video, I'm going to work through some commonly occurring problems that are going to illustrate different aspects that you need to know regarding sequence convergence. So stay tuned.